again. Is it okay?
Yes, okay, great. So welcome back, everybody. Today we're going to start off with a talk by Krzysztof Oleszkiewicz. Thanks. Please start.
Thank you very much. So thanks to all the organizers for inviting me to this excellent conference in this beautiful place. Pity I didn't make it to Berkeley, but I enjoyed listening to the talks previous days. So today I would like to give a talk about my recent work with Asaf Naor. It's not very recent because we started it several years ago, but it took some time, and also a small baby appeared in Asaf's home, so things got a bit delayed, but finally it's published. It just appeared in GAFA Israel seminar. And also it's on archive, so if you want to go and see the details, then it's available at archive in almost the final version. So the starting point is that you have two independent f-valued random vectors, and f in the whole talk stands for a separable Banach space. Let me just mention that this separability isn't a big deal. This is mainly to get rid of all measurability problems. So when you add two independent random vectors, you would like to have their sum also being a measurable random variable and inseparable Banach space. It works perfectly, but actually most of the problems make sense in finite dimensional spaces or can be easily adapted even to some standard non-separable Banach spaces like, say, small L infinity. So it's just a pure technicality to avoid talking about some measurability problems all the way. So now the trivial observation is that if these two random vectors are integrable, meaning their first moments are finite, then the pointwise triangle inequality, which holds for every point of the vector space F, implies after integration the following inequality. So you just integrate both sides, you choose the optimal z or some sequence of z's that's going to give you the infimum, and this is what you have. So this is the trivial bound, and basically most of this research with Asaf started from the question, to what extent can this type of bound be reversed? That was our starting point. And let me just mention that, so when you look at this reasoning here, you don't use independence in any way, right? So it's enough to have just two random vectors x and y that live on the same probability space, and you can do the same argument. But of course, you need to assume something to be able to reverse this inequality, paying, of course, some price in terms of some multiplicative universal constant, hopefully. And you need to assume something because you need to exclude the possibility that x is just identical to y on the whole probability space, but non-constant. Okay, this happens, the left-hand side will be 0 and the right-hand side will be non-zero, possibly, and then you are in trouble, right? There is no hope for inverting this bound. So independence is a natural assumption to exclude just having trivial 0 left-hand side here, unless both variables are just constant. Okay, so this is a natural question. And because this first part of reasoning can be done without the independence assumption, once you get the reverse bound, it gives you also some understanding in terms of what happens when you have two random vectors x and y that are not necessarily independent. So you can take then independent copies of x and y, which themselves are not independent, and you can deduce from this reverse bound and from this trivial bound that actually the independent case in a way majorizes the generic situation. You have any couple of x and y, you choose their independent copies, and you observe from this reverse bound and from this trivial bound that this expression for arbitrary x and y is dominated by the same expression up to some constant with their independent copies replacing x and y. Okay, so this is a natural question to study such quantities. And now I want to have some pretext to say that this fits to the subject of our conference. So we can pretend that this has something to do with concentration for the following reason. You may construct a new f-valued random vector just by taking a mixture of x and y with weights 1/2, 1/2. So you make a new random vector by defining its distribution in the following way. And then, obviously, this expression is 2 times expectation z minus little z. And therefore, the inequality that we deal with can be expressed, the right-hand side here can be expressed in terms of the concentration properties of this random vector z. So somehow you look at the joint concentration of x and y by taking their mixture and asking how well can this concentrate around a single point. Okay, so this is somehow connected to the idea of concentration, and this side tells you something about the joint concentration of x and y, and the left-hand side tells you something about concentration of x around y and vice versa. Okay, so these expressions have something to do with concentration in spirit. Okay, so now for a separable Banach space, we define a number of geometric moduli, and each of them is of some interest, and I will just briefly describe them. So to start with, given some parameter p that is positive, and usually it's at least 1, you define little bp of the Banach space as the infimum over those constant beta for which this inequality holds whenever you have independent f-valued integrable random integrable with p power random vectors. Okay, so whenever the left-hand side makes sense, whenever you have enough integrability, you just ask what is the optimal constant working for any couple of independent random variables. Okay, so this is a legitimate question. What I showed you before is the same question just for p equal to 1. Okay, so now we can ask the same question for p differing from 1. And the use of letter b in this notation comes from some metric geometry, from Riemannian-Alexandrov geometry, and it refers to the geometric barycenter in the context of Hadamard spaces. And the name was invented by Asaf, and to me, barycenter somehow is associated with a different thing, but it has some good explanation in terms of Asaf's previous research in Riemannian-Alexandrov geometry. So this is why the letter B appears here. And now that was actually where we started. Asaf was interested in finding the answer, what is B1? What is the optimal constant in the reversal of this inequality for exponent 1. So actually, it's very easy to prove that for p equal to 1, you can prove this inequality with constant 3. And for p greater than 1, you can prove it with constant 2 times 3/2 in power p. And this is like few lines using only Jensen's inequality and triangle inequality. This is simple. What is interesting is that this is also optimal. And somehow optimality of this constant is much less obvious. At some other conference, I showed with details the construction of an example showing that this constant actually is optimal. I will not repeat this because I know that some part of the audience have seen the proof, and anyway, it's in the paper. I will just briefly sketch how you make an example of the Banach space showing that you cannot beat this constant. So basically the idea is that you try to imitate the metric space that comes from the graph distance on the bipartite graph. So you have, imagine that you have a graph with n white vertices and n black vertices. And the distance between n distinct white vertices is 2. The distance between n distinct black vertices is 2. And the distance between any white vertex to the arbitrary black vertex is equal to 1. So this is exactly what happens when you have a bipartite graph. On one side you have white vertices, on the other side you have black vertices, and edges go only between all white and all black vertices. This is a complete bipartite graph. So if you look on this graph for a shortest path between white and black vertex, it will be just the edge connecting them. And if they are of the same color, you must first pass to the other part of the graph and then come back. Okay, so the graph distance is equal to 2. Okay, but this is a metric space. And there are good reasons to investigate this metric space in context of this question. But how you make it a Banach space, how you embed it into a Banach space. So any metric space can be embedded into little l infinity, every finite metric space. So you just embed this bipartite graph with the graph distance, and then you try to put it in a nice way to get some symmetry so that computations are possible, and then you calculate everything and it doesn't work. Basically that's the starting point. And then you notice that if you put it in a nice enough way, all vertices of this graph, after embedding into little l infinity, may lay on the same hyperplane. You can take, for example, the hyperplane consisting of all points whose sum of coordinates is equal to 0. And when you do that trick, you can prove that if you want to optimize this site with Z needs to have a lot of symmetry between coordinates. Because everything is symmetric, you can use Jensen inequality showing that if you look for the optimal Z in this quantity, it's enough to look at Z, which has first n coordinates equal and remaining n coordinates also equal, but with a minus sign. So if for first n coordinates of Z, you have some value u, the remaining n coordinates of Z will have value negative u. In this way, you restrict the Z's that you need to consider to a very small subset, and then proving the inequality, proving that you cannot get a better constant than 3 for p equal to 1, or in general that you cannot beat this quantity 2 times 3 over half in power p is relatively simple. Okay, so that's the basic idea. You first take the bipartite graph with the graph metric, then you try to embed it just to get into the Banach space setting, and then you realize that your example doesn't work in the L infinity as a whole, but then you just cut this L infinity with some hyperplane, and then it works. Okay, so that's basic. And then you pass with n, which is the number of vertices in this bipartite graph, to infinity, and you prove asymptotically that you cannot beat this constant. So that's the basic idea of the construction. It's a bit laborious to show it in detail. So because I have already showed this at some other conference, and many people from the audience saw it, I don't want to bore them with repeating this. Okay, so that was our starting point. But on the way to getting the understanding that this is the right constant, actually Asaf and I got annoyed for a while because we tried some other counterexamples and they didn't work. Whenever we had some favorite space and we tried to prove that, well, you can do better than, you cannot do better than constant 3 for p equal to 1, we failed. So of course we started to think why we failed all the way along trying to find a counterexample, to find the example showing the optimality of this constant 3 here. And we realized that this has something to do with the geometry of the space. And we tried to prove some positive results, showing that if you assume something more about this Banach space F, then you can get a better constant in this inequality. Okay, so that's another part of our research. After realizing that this is the optimal constant and providing an example, indicating that we looked for some other approach to get some better constant under some additional assumptions. Okay, so now let me sketch some other geometric moduli that we chanced upon in our research. So this slide is sponsored by the letter M, which stands for mixture. And now we look for the same inequality, but instead of the arbitrary small z from the space F, we just look at the average, the arithmetic mean of expectations of x and y. So here it's natural in this context to assume that p is greater or equal to 1, because then it ensures the existence of the expectation. This is a natural setting. And now you ask for the same inequality, but restricting your attention to a particular choice of z equal to the average of expectation x and expectation of y. And of course, you can rephrase it using this mixture random variable z that I discussed before. Then this average of expectation is clearly the expectation of z. You can rephrase this inequality in this way. And there is an obvious observation, just because this is the special case of the choice of little z, always you have this inequality, okay? So that's another natural question that you can ask. And we made some research in this direction. I will briefly state some results in a moment. And then another term is roundness. So given some positive parameter p, which also usually will be at least 1, you can define Rp in the following way. You take x and y, which are independent, and then you take their independent copies. So x prime has the same distribution of x as x and is independent of x, and the same about y prime. And then you can try to bound this expectation by this expectation, and you ask what is the optimal constant R here, how small R you can take. So this type of question comes from late, maybe not so late, second half of the 20th century, and Per Enflo was one of the first, and perhaps the first person to study this type of inequalities in his study of the geometry of metric spaces, and he called this roundness, and this is a natural way to somehow inherit this naming for our proposals. So this is the parameter Rp. And the last moduli will be called the JP for Jensen. And now it will be the supremum because the constant stands on the left-hand side, on the small part. We look for the optimal J in this inequality. So Z is a vector valued random variable, a random vector with values in F. And actually, in many applications, the Z that appears here will be exactly the mixture of X and Y that appeared before. But we can also ask this question in general for some generic random vector Z. You assume that this is integrable just to give sense to expectation. And you ask what is the best constant with which this inequality holds. And you call this JP. And by Jensen's inequality, obviously this always holds with J equal to 1. So the question is, can you strengthen the Jensen's inequality? Can you get the constant better than 1? And now let us observe that there are some relations bounding this moduli. So one trivial observation was that BP is always not greater than MP. And another observation, a bit less trivial, is that MP is always bounded by 2 plus RP divided by 2 times JP. And now let me explain this. So you look at this expression. This is just JP for X and Y. This is expression of the type that appears in the definition of M. You see, this is exactly this type of expression. So you take this and notice that this is just twice the expectation when you replace X and Y by Z. This is just because Z is mixture of X and Y with weights 1/2. Then you bound this by this just by definition of the parameter J, because you have this inequality. Now, because you know that Z is the mixture of X and Y, and Z prime is a mixture of independent X prime and Y prime, you can easily write down this expression in terms of the distributions of X, Y, X, X prime, Y, Y prime. There are just 4 cases, and 2 of them glue together to form this. And then you recall that you can bound this expression with constant RP by this expression, by definition of the roundness parameter, okay? So putting things together, you get this inequality. And of course...
May I ask about this roundness constant? Why are you calling it roundness? Is it the case that it's minimized for Hilbert space or something of that sort?
Yes and no. I'm not an expert in roundness, but basically that was the parameter that Enflo invented to show that some metric spaces cannot be embedded in some other metric spaces. So the way you do it is you prove that some of them have this with nice constant and the other spaces don't have it. And it's called roundness because, yeah, being in Hilbert space, for example, gives a good estimate for this parameter. But I'm not in a position to say whether it's optimal for Hilbert spaces or anything like that, perhaps. But I'm not an expert in metric geometry. So
thanks.
But probably if you ask Asaf now, he will know in a second, okay? I'm just not doing this type of research, so I don't know at the moment. Okay, so now, of course, the interesting question is, what can you say about these parameters? And they are interesting not only from the point of view of the metric or Banach space geometry, but also they are interesting from probabilistic point of view. They say something about symmetrizations of random variables, and in many applications in probability, you want to replace, for example, this type of centering of a random variable by this one, and it's good to know how small price you can pay for replacing one with another. So this is a natural probabilistic question as well, appearing in many applications. So we managed to establish the exact values of some of those parameters for some particular Banach spaces. So one example is LQ space, just the Lebesgue space of functions integrable with Q's power. So for JP, we have the full range of exact values. So whatever P and Q you take from 1 infinity half line, the JP can be expressed as 2 in power C, where C is given by this formula. Okay, and we have examples showing that this is optimal. And because there are 4 expressions that can appear here, there are 4 quite different examples showing optimality of this bound in various regimes, in various relations between P and Q. Okay, depending on what P and Q are, you have various examples showing the optimality of this. And we managed to prove that with this constant, the inequality always holds. So for P and Q between 1 and 2, and when P is below Q, we managed also to find exact values for these parameters BP and MP. Now, for the roundness parameters, we managed to do in some special cases. So when P and Q are between 1 and infinity, and one of them is between the other one and the conjugate Hölder exponent. And also there is some additional special case where we know that the roundness parameter is equal to 2. So of course, I'm not going to show you the proof. And of course, there is no hope for you to remember what these parameters are at the moment and what this means. But basically, this is just to show you that in quite many situations, you can find optimal constants. And besides those situations where we can prove that the bounds are optimal, that the values of these parameters are exact, we also have some one-sided bounds which look reasonable and work in more general situation outside these assumptions. But then we don't know whether they are optimal, or we have good reasons to believe that they are not optimal. Sometimes we conjecture some better values. But again, we don't have time to get into technicalities. I would like just to give you some sketch of the idea how this thing is proved. So the idea comes from complex interpolation. So when you want to prove such bound on the geometric moduli for the space LQ, it's convenient to express it as an interpolation space between L2 and LQ for some capital Q. Okay, so when Q, small q, is bigger than 2, then capital Q, of course, also needs to be bigger than 2 and possibly equal to infinity. When small q is between 1 and 2, this capital Q is below 2 and possibly equal to 1. In many situations, it will be equal to 1. So the second point is to choose the right operator. And it will go between these function spaces. And choosing the right operator is important because later you want to deduce something from the interpolation bound that you will get. And then you need to prove that this operator that you choose satisfies a simple L infinity norm bound or L1 norm bound. And when I say that it's simple bound, it means that you prove it using just the triangle inequality. In all our attempts, we are not able to get any more sophisticated tool to deal with this, this part of the estimate, basically because you don't have any information about this LQ space in most situations that you could take advantage of. And then you do another estimate, which is usually more subtle. And this is in Hilbert situation. You use spectral methods and you prove the norm bound, norm estimate for L2, L2. Okay, so now this is a misleading notation. This LQ that is inside, or L2 that is inside here, is a function space. And you look at the operator that goes from this function space to this function space. And to make things more difficult, they may live on different measure spaces. Okay, so this is LQ on some measure space, and this is LQ on some other measure space. And then you look at the L infinity bound for a vector operator going from this vector space to this vector space. Okay, and for this, and of course, everything needs to be complex Banach spaces, and then you can use complex interpolation. So this is like restoring. The difference is that in the classical restoring, you have just complex valued functions, and here you have vector valued functions, and you need to use a bit more advanced tools, but of course they are well known, they exist, and you just apply the ready toolkit from the interpolation theory. Okay, so now once you have this L infinity, and L2 bound, you can use the interpolation theory to get LP, LQ norm bound just by restoring equivalence for these vector valued spaces, vector valued operators. Now, once you have this bound, you deduce from it some information about the geometric modulus. So this is where the choice of the right operator is important, because you need to choose it wisely in order to be able to deduce anything here at the step 4. Okay, now if you are lucky, you may manage to show example showing that the bound that you obtain here on the geometric modulus is optimal. So in some situations we are lucky to prove that. Sometimes we think it's not optimal, but if you are lucky, you can prove this. Then the next point is that sometimes it works better if you use the interpolation trick not for the modulus that you want to estimate, but for other moduli, and then only after making interpolation you take advantage of some relation between moduli. So let me give you an example. So this red inequality is one of the examples of the interplay between moduli that you can take advantage of at this point. And surprisingly, it works better in many situations than using just interpolation for the modulus that you want to study. Okay, so this is another thing. And then you still want to improve the obtained bounds in some situation, and sometimes surprisingly, you can do it by some other tricks involving nonlinear isometric embeddings. So there are some results showing how to embed LQ into some LR for some other exponent, but not in a linear fashion, but by using some power maps that are nonlinear but are isometric. And because all expressions that you deal with have the property that they are of the distance type, all expressions here are just metric type things, measuring distance between two things. There is no problem with the fact that this is nonlinear, and these nonlinear isometric embeddings may give you some extra power in many situations. So this is actually, if you look at the details of our paper, you will see that in some places these nonlinear isometric embeddings actually allows you to get something much better than if you don't do that. Okay, and at the end, I want to mention that the same idea may be exploited when you deal with Schatten classes instead of LQ. Okay, so this is non-commutative counterpoint of Lebesgue spaces, and because you can express the SQ Schatten class as an interpolation between the Hilbert space and the S infinity, the operator norm Schatten class, you can repeat the same scheme of the proof. The important thing is that in Schatten classes for parameter 2, you also have a Hilbert space situation, and you can apply the same spectral methods approach and get also the results for Schatten classes. So all this idea has a Schatten class counterpart. Unfortunately, for Schatten classes, many estimates that are effective and optimal for Lebesgue spaces are no longer optimal, and the question is what you should improve to get something even better in non-commutative setting, but we didn't manage to make any progress in this direction. So now let me just give a bit more details about this interpolation picture. So you have some operator that you want to bound. So this is this wisely chosen operator that you really want to estimate. So you have some function space LQ on some measure space. On the right-hand side, you have LQ on some other measure space. Sometimes it will be the same, but quite often it will be a different measure space. And then you want to bound the operator T acting from here to here, and you want to bound its pth norm. Okay, so this is how you interpret this arrow. And how you do that? You express LQ as an interpolation between capital LQ and L2 with some parameter theta. And you do the same with L2 and L infinity here. You choose the theta so that both equalities that come from this interpolation theory, this is very restoring-like, that both of them are satisfied for the same theta. And if you are able to find such theta in the interval 0, 1, that this is satisfied, then you can bound the norm of this operator as some geometric mean of the norms of these operators, and the powers in this geometric mean expression are related with theta. One of them will be theta, and the other one will be 1 minus theta. Okay, and the similar trick works when p is between 1 and 2. This is what you do when p is between 2 and infinity. And if p is between 1 and 2, you just dualize the picture and basically do the same, replacing L infinity by L1. The same idea works, okay? And the main caveat here is that, of course, you have some freedom. You can change this parameter theta and capital Q. And when you play with these two parameters, trying to make things work together, you must be careful because you cannot go with Q above infinity and you cannot go with Q below 1, okay? So this is the main reason for different areas of applications of the results that appear. You notice that there is some interplay between parameters P and Q. If one of them is greater or greater than the other one, greater than conjugate to another one, or some other relation between happens, then you have this bound. In other regime, you have another bound. And the reason, the basic reason for the results splitting into subcases is exactly this obstacle, that you cannot do this trick with Q greater than infinity or below 1. Okay, and actually there is a good reason for that in many situations, because what you get just by stopping at the level of Q equal to infinity or Q equal to 1 gives you the optimal constant, and you can show an example indicating that actually you cannot do better. So you are lucky, somehow the formalism stops you, but it's good that it stops you because it gives you the optimal result. Okay, somehow the interpolation theory does the job for you. Okay, and now let me just demonstrate, because all of this is quite vague. You didn't learn about what is this wise choice of operator to give anything. And I will just show you the simplest example how to choose this operator to make the thing work, okay? So let us start with this random variable z. It is defined on some probability space omega mu and takes value in some Hilbert space. Okay, so let's start with the Hilbert space valued operator. So now we have the space of all age-valued functions, age-valued random vectors, but defined on the product space. You take omega product with product measure, and then from this space of all such random vectors, you take the orthogonal projection to the closed linear subspace of functions living in this space of a very special form. This very special form is functions of the form phi of x minus phi of y, where phi is just function of one variable. Okay? So you look at the functions that are symmetrizations themselves, and you project from the whole space to the linear closed subspace of these very special functions. Okay? So you can express S of f as Tf of x minus Tf of y for some Tf, and one can easily check that this Tf may be explicitly expressed in terms of some integral. You just integrate function f with respect to the second coordinate. You average it with respect to first coordinate. You take the difference of this expectation, 1/2 of it, and this is an easy exercise that this orthogonal projection is given by function of this type. Okay, and here additionally you want this function phi to have expectation 0, because of course if you move it by constant, if you add constant, the difference will not change. So just to keep attention to the specific single function, you additionally assume that it has expectation 0. Okay, so then you can find Tf by this expression, and actually you see that this is linear. So this is our operator. This is our operator that we want to study. And now you see this lives on a product space, and what happens on the first coordinate is independent from what happens on the second coordinate. So if you will, instead of looking at x and y, you just can speak about z and its independent copies. And these are just independent random variables, okay? So they are orthogonal in L2 because of the independence. So now we have this trivial inequality. This comes just from the fact that S is the orthogonal projection, so it doesn't increase the L2 length of the function. Now you know that SF can be written as this difference. And now you know that these two summands are independent. So the squared norm of that is just squared second norm of this plus squared second norm of this. This is just Pythagorean theorem, okay, because of the independence. And this is the wise way of writing the dependence on the first coordinate only, and here the dependence on the second coordinate only. So somehow this is more formal way of writing this thing here. Okay, but now you notice that because this doesn't depend on the second coordinate and this doesn't depend on the first coordinate, you can easily compute this just in terms of what happens on the first coordinate. Okay, so you managed in this way to bound the L2 norm of Tf, which lives on just single omega, in terms of what happens to the function f on the product space omega omega. Okay, so we have proved this estimate. Okay, we have bounded the norm of operator t given by this formula by 1 over square root of 2. Okay, but then we can look at the operator given by exactly the same formula but for arbitrary Banach space. So here we employed the fact that we live in a Hilbert space and we could use orthogonality. But now for arbitrary Banach space, we don't have these spectral tools. So the only thing that we can do is just the triangle inequality. We very bluntly just estimate this from above by the triangle inequality, observing that this norm is bounded by 1 and this norm is bounded by 1. And then we are in position to interpolate. This is exactly part of the picture that I showed you before. You have L2 on some measure space. Here you have L2 on some other space. And here on the same probability spaces, you have L infinity bound. So we can interpolate between L2 and L infinity. And here you can interpolate between L1 and L2. And in this way, you get exact values of JP for arbitrary choice of P and Q between 1 and infinite. Okay, so this is what I call the appropriate choice of operator T for the purpose of getting the bound, because now we are able to make the last step and just use this norm bound that we obtain between LP and LP for a very specific function. So we have this, so here we have constant that is smaller than 1. This is some power of 2. Here we have some constant that is equal to 1. So when we interpolate, we obtain some other power of 2 with exponent that depends on P and Q in the way that I described a few slides ago. And then you apply this LP norm bound for a very specific function f of xy, which is just random variable z at point x minus z in point y. And you can easily see that for this random variable, Tf is simply z minus expectation of z, because this expression zx minus zy is the same as zx minus expectation z minus zy minus expectation z. So from the very beginning, this function lives in the subspace on which we projected. So nothing will change, and Tf will be exactly the centered version of z. And then the interpolation bound that you obtained here gives you exactly the J inequality that we are looking for. You bound this expression by this, and the constant that you get, luckily, is optimal here. Okay, so this was just to give you the proof in the simplest case. For other moduli, the proof is more complicated, and I don't want to get into details. They are written in the paper. The paper is like 20 pages long, and I don't want to bore you here with technicalities. It's more tricky. With other moduli, you need to get some more complicated operators, to use some additional tricks to get some interesting results. But basically, the main idea lying behind this is this interpolation machine. And now, just as a teaser to make you have a look into the paper, I will show you the following result that is also contained here. So when you have a Banach space that is of real dimension at most 3, the following bounds hold for arbitrary random vectors n, x, and y. You need to assume something about integrability just to give sense to both sides of the inequality. But once you have integrability, the following bounds hold true. Okay. And instead of assuming that the dimension of the Banach space is not greater than 3, you can assume, for example, that this is Hilbert space. And also you get these bounds. And I cannot see any easy reason why this is true. Okay, I know, of course, how to prove it, but I think it's a bit surprising that you have this type. Of course, this is some limit case when you look at the p powers and tend with p to 0. Okay, so then you come to this type of questions. Technically, they are more difficult than the questions for p greater than 0. You need to take care of the fact that logarithm has two singularities, both in 0 and in infinity, and this makes proofs much more complicated. And basically the idea allowing you to prove this comes from the very beautiful results by Carlton, Koldowski, Jaskin, and Jaskina, that any three-dimensional Banach space, as well as any Hilbert space, embeds linearly into L0, and L0 here is understood as the function space with the norm given by geometric mean. Okay, so for a function, you take expectation of logarithm of the absolute value of this function, assuming that it's integrable enough, and then you take expectation of this. So I put isometrically in quotes signs because, of course, the L0 here is not a metric space. And actually, it's so bad that you can have two functions f and g for which this L0 norm is equal to 0, but their sum f plus g has this L0 norm positive. Okay, so it's not only the matter that it doesn't satisfy the triangle inequality. It's not quasi-metric, but also it's so bad that the sum of two elements that have 0 norm may have non-zero norm. But still, you can give some good meaning to isometric embedding of the Banach space into L0, and the beautiful and difficult result from harmonic analysis shows you that you can do it always for three-dimensional spaces. And also an easy fact is that Hilbert spaces can be embedded in L0. Okay, so thank you very much. This is all that I wanted to discuss.
So any questions for Krzysztof? Actually, I'll ask a question. I don't know if this is a very sensible question, but with discrete random variables, if I want to have some, so random variables dependent, I can not dependent by looking at something like mutual information.
Mm-hmm.
Oh, okay, and I can quantize just how dependent they are, right? I can say if they're mutual information.
Mm-hmm.
Epsilon, then they're most independent. So I'm curious, is there a robust version of reversal in the beginning where if you somehow can bound quantitatively the amount of dependence between x and y, you can still reverse it with maybe a worse constant or something like that?
Okay, I didn't hear your question in full because I had some sound problems, but I think I understand. You ask whether you can relax the independence assumption to some sort of almost independence, okay? And I think this is a very good question. This is a question how much you need independence in all these reasonings, okay? And I don't know an answer to it, and I think it's worth studying. What is the natural condition replacing independence in all this stuff, still allowing you to reverse the inequalities? This is a very good question, and I'm pretty sure that you can relax independence. The question is there some natural condition that works as well? But
I was wondering this actually at your first slide, but I was thinking more just letting correlation on one by absolute value, if you let correlation to be.
But what do you mean by correlation? If they are in Banach space, of course, if they are on real random variables, you can say what correlation means, but in Banach space.
I mean, you can define, you can look at the norm, I guess, look at the correlation of the norms. I mean.
That's probably too little. Perhaps you can look at all linear functionals and ask about correlation of phi of x, phi of y for any linear functional phi, for example, or something like that, perhaps. But no, I think that would be too weak. I don't have any ready counterexample, but I think that it doesn't seem likely. This correlation thing would work well for the Hilbert regime, for p equal to 2 probably, and for Hilbert space, but I don't see any reason why it should work for other powers and other vector spaces. I don't think that that's the correct way of looking at that. I think your questions are very natural, and I don't know any good answer. And I think that's one of the reasons why this is worth studying this question, because as I said in the beginning, the question is you want to somehow majorize, having a distribution of X and distribution of Y, you try to understand in what position you should put them to get the maximal or up to constant maximal value of this type of expression, okay? And the answer is that they are independent. This is basically what our results show. And the question is what you can do instead of independence. And of course, if you can do this with condition different from independence, then again, you have two-sided inequalities going both directions. So this means that such condition would be basically equivalent to independence in terms of this majorization, okay? So this is a very natural question, a very good one, and I don't have any idea what this condition should look like. I think this is a very good question, but maybe it's hopeless. I just don't know. Maybe some mutual information, something like that, as Jelani said, but I don't know.
I have a comment and a question, Krzysztof. Comment is, I think part of what Jelani was saying, I couldn't hear it completely either, but if you look at discrete random variables, are there inequalities like this using mutual information, which is another way of comparing how independent or non-independent they are, right?
Okay, so you say that there is something that is already known in this direction.
No, I think Jelani was asking.
I'm sorry, I guess some of my question maybe wasn't heard. Yeah, I know examples that have nothing to do with this kinds of expectations of norms, but just inequality. Let's say that something is true for independent random variables. If you bound the mutual information, can you still say something? I do know examples of that don't look anything like this. So I was just curious whether in this particular example there's some quantization of dependence that can robustify the theorem.
I think this is a very good and natural question, but I don't know an answer to it, and I would be glad to know something more about that, but it may be difficult.
I have another quick question, Krzysztof. So for the general bounds you mentioned between M and B, BP and MP and R, so those are the only general bounds for every Banach space F? There is no,
well,
up to some other constants depending on maybe P and so on. Can you reverse some of those?
I think this study is very far from complete. So we tried to optimize in the direction where we knew what we were doing, right? Where things work smoothly, but we are far from having, full set of relations between these constants. They are interesting geometric moduli, and one of the reasons we didn't go too much into this abstract nonsense is the fact that we still don't know what is BP or even B1 of little L infinity. Okay, L infinity is not separable, so think about high dimensional but finite dimensional little L infinity. Okay, as a unit ball, you take just the high dimensional cube, and we don't have any idea what B1, what this basic question, what the answer to this basic question with exponent 1 is in this case. Okay, if we get this additional cutting with hyperplane, then we know. But even for L infinity, we don't know a thing. And if you don't know how to answer such very simple questions, somehow getting too much into abstract interplay between these parameters probably is not the good choice. Probably first one should understand the basic examples, and even here in many situations we don't have a hint what the answer is.
And for all P, for B sub P, you have the same construction that shows the tightness, yes?
Yes. So in this bound, this is basically the same construction, and the only thing that differs in the proof is that once you use just the Jensen inequality for the norm when P is equal to 1, and if P is greater than 1, you just use the convexity of the norm in power P. But the underlying structure is the same.
Thanks.
Basically. And perhaps it's interesting to know that for P greater than 1, you can ask the same question in the language of metric spaces instead of the Banach spaces, okay? All three terms that appear here can be expressed in terms of the metric distance between x and z, y and z, x and y. And we can answer this question about the optimal constant if you replace Banach spaces by metric spaces. It's different from this one. If P is greater than 1, these two bounds match for P equal to 1, and somehow the metric space case is trivial compared to what happens in Banach space. Somehow it's not very difficult to prove the optimal constant, to invent what it is, and also to prove the optimality. Somehow the metric question here is much easier than what happens in Banach space.
Okay, thanks a lot, Krzysztof. I think we're actually now running into the next speaker, so let's thank Krzysztof for his
thanks.
talk.
Thank you.